Actually, I'm going to move these. I realize I should move the chairs because I walk around a lot, and camera people never like it, but that way I can see everybody. Let's see, let's turn this off. There. Cool. Thank you, everybody, for coming. Thank you, hardwear.io. If you've ever run a conference before, you know how hard it is to actually run one. I do not envy what they have to go through to put this stuff on. So it's really nice to be back in person with people. And yeah, all the work that Ontrix is doing and all the team behind it, it takes a lot of effort to make this happen, right? So it's really cool that they did it and that we're all back together. And it's especially nice to be at a hardware specific conference because it's kind of like our own type of people, right? It's not like you have 30,000 people that are all doing different things. Like, this is really nice to be able to see a lot of familiar faces, a lot of new faces that are all interested in hardware. And especially for me, being up here, seeing a lot of people I know makes the talk even harder for me, but this is cool. I know it's going to be scrutinized a lot more. Okay. So yeah, my name is Joe Grand and, I hack hardware. This presentation kind of came together. I wanted to just have some like fun pictures of some of my experiences recently hacking different types of hardware, just to kind of get us warmed up for the event, because there's so many amazing talks. And I figured like, well, let's just show some pictures, right? It's like a little picture show. I know there's a lot of different ranges of skill levels at the conference as well. So some of you will have seen this stuff and been like, that's not very groundbreaking. And then some of you will see this and be like, oh, that's crazy. I want to learn about that. And this is the perfect place to do it. So it really shows like the reality of when you're hacking on hardware. Sometimes it's hard. Sometimes it's not. Sometimes you use simple methods. Sometimes you don't. And it's just this whole range of experiences. And that's what makes hardware hacking so fun. Let's see. Okay, which button am I pressing? All right. So I was never into cryptocurrency. I hadn't really paid attention to it at all until I got an email last year. I think it was, what is it now, 2022? So I think February 2021, I got an email from somebody that was like, hey, I have some money, $2 million locked on a Trezor hardware wallet. Can you break it and get my money back? I can't remember the PIN. And it was a well-written enough email that I didn't just ignore it, because I get a lot of email. And this one was, seemed like it was decent and did not seem like a scam or anything like that. So I ended up talking with the guy whose name was Dan and got his whole backstory and realized, yeah, like he was an early adopter in this stuff and invested some money and just threw away his recovery seed by accident, forgot his PIN, and really needed help. So that's what kind of brought me into things. So I know some of you are probably sick of hearing about the Trezor. It's been hacked a lot. And one of the main reasons I took this on, well, it was still during COVID and I wasn't really traveling and doing anything else. It was like, okay, my wife was like, why don't you just do it? But the other reason is there had been a lot of work already about hacking Trezor devices in various ways with different types of firmware. Kraken had some work out. Wallet.fail had some work out. Ledger had released some stuff about it also. So I was like, I can just replicate this work. Like, it shouldn't be that bad, right? How hard is it to replicate work? And that turned into like 3 months of trying to figure out everything and piece together what was publicly available versus, kind of the reality of doing it on a device that I couldn't mess up on, right? You really only had one chance to do it. But it was a great learning experience, which is really ultimately the goal, right? Is like to do this stuff, to be able to hack and use your skills to help people, but learning along the way. Like, if I wasn't learning something new every time I was hacking something, I wouldn't do it, because I think it would just end up being boring doing the same stuff over and over again. So that's what keeps me going. Here's the setup for it. And there's a couple different pieces for this particular attack. One of the main things about fault injection, and that's what we used for this, the STM32 that's on the Trezor has a couple different security states. There's RDP2, which is the maximum security, no debug interface is supposed to be available. The datasheet even says, like, irreversible. If you set RDP2, you're never going to get access to the chip, which obviously is wrong. There's RDP1, which gives you debug access, but only lets you read the contents of RAM, of like the volatile memory area, not the flash, where normally we want to go after flash if we're getting firmware or some sort of persistent storage like recovery key and stuff like that. But it was still a downgrade that could potentially be useful. And then there's RDP 0. To downgrade from RDP 2 to RDP 1 requires a fault injection of basically at the right point in time while the chip is executing its boot ROM to kind of set the state of the chip, you can glitch it, downgrade it, and then in this case, this particular version of firmware was loading the recovery key that I needed from flash into RAM, and because now I had access to RAM through RDP 1, I could read the contents. So it was pretty cool. So I used the PHY Whisperer as part of the process. The chip is only checking the state of security when it's resetting its boot ROM and executing its boot ROM. So I'm using the PHY Whisperer, which is a really cool like USB protocol analyzer tool, where you can monitor USB traffic and even like set a trigger when certain data comes across. But I was just using it to power cycle the board. I do have references, by the way, to all the hardware stuff. I have links at the end, and I'll put the slides up on my website so you can actually click on the links. But this is just a really cool tool, and I'm just using it to power cycle the device in an easy way because I can control it through Python and just power cycle and then try to do my fault injection, which is done with the Chip Whisperer. If you haven't gotten into fault injection before, it's sort of like once you learn how to do it, you want to just inject faults in everything. You want to glitch everything. It's like a hammer, right? You have a hammer and you want to either like bash a lot of things or you want to like build a lot of things with it. Once you know how to do fault injection, which you might be able to do some exercises in the other room, I'm not sure, but there definitely talks about it over the next 2 days. It's just a really, really cool way to cause system to misbehave in a way that you can take advantage of. Very, very cool. And sometimes you can't take advantage of it. You just cause the system to fail. But really cool. So I'm using the Chip Whisperer. There are other devices as well that are available. There's from Thomas Roth, also known as Stack Smashing. There's the Pico Debug and Dump, which is like an easier, kind of simpler, lower cost open source method of doing glitching. There's some other lower end versions of the Chip Whisperer tool. There's a lot of other ones as well. So if you don't want to go, full on commercial, you can still kind of get into it. And then I have the Sager J-Link, which is my hardware interface that connects to the SWD interface, the serial wire debug interface of the Trezor, of the STM32, which in theory isn't supposed to be accessible at all. But when you downgrade and you properly inject faults, then that's how it works. So I'm not going into full on details, but just, to kind of see the different tactics that are needed to break stuff. When you're doing fault injection, especially voltage fault injection, where you're basically taking the core CPU voltage or some other voltage on the chip where you want to affect operation, you usually need to modify the target in some way to make it more susceptible to fault injection. Most embedded systems, most electronic devices are going to have bypass capacitors on all of their power rails to kind of smooth out the power. So if there is noise in the system or a dirty power supply or something, the chips are still going to operate properly. So we want to remove those capacitors from the system. So when we do our fault injection, the capacitors don't smooth out those very minute signals, the very minute glitches that we're doing. So here's a picture of the Trezor 1, and kind of showing some of my notes of where things connect. So like the PHY Whisperer is going to the USB connection for the power cycling. Because the Trezor is open source, it makes it a lot easier to kind of just grab their schematic and see, okay, where do I need to modify things? If a device is not open source, it's just part of the reverse engineering process to figure out how the board was designed, how the traces connect to different signals. There's a saying like, every piece of hardware is open source if you have physical access to it, right? Because you can figure this out, but being open source just makes it a little bit easier because I'll just go to GitHub and grab the schematic. So yeah, the J-Link interface for the serial wire debug. And then since I knew that I wanted to target the core voltage lines of the STM32, that's where I started looking for the capacitors to figure out, okay, which ones do I need to remove to give me access to that core voltage and have it not filter my glitches. So there's just two capacitors I had to remove because there's two different core voltage lines. I also removed the one from the reset line because the reset is what we use as the trigger to know when the chip starts executing its internal boot ROM. And there's a capacitor on there which kind of slows that down. So I just took that off. So it's a much sharper edge that we can use to start our timing for fault injection. where really, even without that, like you still have to run a range of different kind of glitch attempts within an area to try to hit it, because it's never gonna be the same exact spot. It might be within a range, and you can do that very quickly. But there's all sorts of, silicon variances with manufacturing processes and ambient temperature and things that are gonna kind of change stuff. But anyway, yeah, so like prepping the board with, removing those capacitors, put my SMA connector that then connects up to my glitcher. So if you want to try to replicate some of this work, this is all you have to do to prep the Trezor. And then you'll need some code to actually go and cycle through, delay after the reset line goes high, and then start doing your glitching and see what happens. But this is kind of the starting point for the hardware. So this is it looks so angled from here. I guess that's on purpose. This is a screenshot of my oscilloscope when I was doing the fault injection on this original Trezor. So this was last summer, and we can see the glitch. This is on the core voltage line of the Trezor that's going to the STM32. And at some point after reset, I think it's like 150, 160 microseconds or something like that is when I do my glitch. And that causes the system to basically either skip over or just downgrade, basically have the STM32 say, wait, I guess I'm reading a value that means I should be in RDP1, not RDP2. And here's a little video of it. So we can kind of see my original implementation was pretty slow. It was like 1 a second, maybe. And then since then, I've hacked a bunch of other Trezors and I've just sort of, enhanced this a little bit and can run it a lot faster. So it makes it a lot easier to figure out like where do I need to glitch and then, do the glitch faster. Cause this took me like probably 3 or 4 hours of sitting there waiting for this thing to hit, and now I can do it in a couple of minutes. And basically what I did is the original version, I'm using the Sager JLink command to query the STM32 and try to connect to it, which is like a very verbose, long process. And I realized that I can use the Sager JLink in a lower level mode to do like a low level JTAG ID code attempt of just connecting to the JTAG directly, shifting data out of the data register and reading if there's an ID code or not. And by doing that, you can very quickly detect if a debug interface is available or not without going through like this whole long process. When I started doing the work, my wife was like, you need to be filming this, because a lot of the videos that I make, if you've seen them before, are pretty bad. Like I hold my phone and I'm like, hey, it's Joe Grand, here's a thing. And it's very engineering focused and talking to my friends about what I'm working on or some tips or whatever. And then the professionally produced videos I've done are all engineering related. So not hacking related, but building related. She's like, you should film it. So I ended up calling a friend of mine who's a professional cameraman who had filmed some of my engineering work. And he came by and actually filmed the real process when Dan, the customer, flew all the way from New Jersey to my house. And so we did like a professionally produced video about it. And then I had a friend of mine, an old client of mine, who's now a business partner in our wallet hacking journey, do directing of the video remotely. So he was on FaceTime, kind of set up the shot here, ask these questions. But we filmed the real hack in real time, and the video is up on YouTube. It was released in January. So if you haven't seen it, it's really fun to watch. But it shows a lot of the kind of real drama of when you're doing this. And there's nothing fake about it. So there's comments on YouTube. I don't read the comments, but people have told me there are comments of like, people think we're, that's a good, if you take nothing else from this presentation, don't read the comments. It will just be so much better for your mental health. But yeah, people are like, oh, they totally faked it because they're smiling, right before they did the glitch. And it's like, no, we were watching Simpsons cartoons and we just couldn't show that in the video. But it was real, right? Because we wanted to show the reality of this. And it was a lot of fun. So yeah, check that out. In parallel to doing the voltage fault injection, I was kind of exploring a lot of different options because I wanted to make sure I had backup plans and contingency plans for different types of stuff. So I started also working with EMFI, electromagnetic fault injection, using the chip shouter, which is one method of doing, it's over there. Chip shouter's over here. Yeah. So one method of doing fault injection, basically generating electromagnetic fields in a coil and kind of passively injecting those onto the device, which will induce voltages or currents on the die. So a destructive technique where you don't have to usually modify the target at all, but you can still affect some sort of problem or misbehavior that you can take advantage of. Colin O'Flynn had done some work about using EMFI with Trezor devices up to version 1.7.3, I believe, which was a WinUSB driver. And basically, he was using the Phi Whisperer device to monitor the USB, basically the enumeration process. When you plug in the device to the computer says, send me your, some descriptor. I can't remember which one. And the USB device will send back some packet. So if you glitch at just the right time, the device, instead of sending its normal packet of whatever X bytes, you glitch it when it's reading the length that it should be sending. And you can actually send like 32 kilobytes or 64 kilobytes. So basically it sends its report descriptor and then it just keeps dumping data from from Flash. So Colin realized that he could monitor the USB communication right when that report request was happening. This would trigger the chip shouter, and then that would do the EM glitch over this device. And then if you get it right, the device dumps its entire flash, or enough of the flash that contains the metadata, which is the recovery seed and some other things. So very, very cool. And he had helped me out with this. He had actually sent me a chip shouter. I went to a surplus store in my area up in Portland and found this like XY, I think it was like a microscope or like a lab XY table. So you can move stuff very, very, very finely. And there's like little knobs to kind of adjust stuff. So part of EM glitching is, besides trying to get the right characteristics of when to glitch and the strength of the glitch, all those things, you also have the physical element of your XY coordinates and your Z coordinates and which coil do you want to use to generate, which way does the magnetic field want to go. So a lot of like physical phenomenon stuff to mess with also. Really, really fun. And so I built this platform, had the Trezor on there, and just basically moved the device around until I could find some interesting behavior. And I was able to replicate his stuff, but it turns out that the Trezor that I was hacking was an earlier version of firmware that wasn't susceptible to this. So it was still fun to learn this. And EM fault injection is, very exciting also. Colin made a device called the Pico EMP. Yeah, Pico EMP. So it's a kit that you can build to do very basic electromagnetic fault injection. So if you want to get into this stuff, but don't want to go commercial, you can build your own, kind of hold it over devices and see what happens. And you can do it above the case. Sometimes you have to open the device and do it to the case. It just depends on the device. But here we can kind of see some fun results of attacks that didn't work. A lot of times you just don't know what's going to happen. So there's like all sorts of crazy stuff on the screen. So I don't know what it affected during the program flow, but it was like drew something to the screen and then drew a bunch of other stuff to the screen. So it's like a bunch of error messages and stuff in there. This one says, please unplug the device detected, which was like, huh. And then there's just a bunch of weird characters. So you get a lot of those responses, which are just kind of entertaining. And then it's like figuring out how to properly do it and get the right timing where like sometimes it just works. And even if you have the right position, 99.9% of the time, you're still not going to successfully hit it. It's just kind of luck with all of your other reverse engineering and combinations of stuff to get it. But yeah, a lot of fun. So I did that kind of in parallel. And then another option for the STM32, which is really funny because the device is known to be vulnerable, and ST Microelectronics knows about it, and there's billions of devices, not just hardware wallets, that use it, but they haven't fixed the problem, and I'm assuming that they haven't because they want to force people or guide people to use more secure devices or better devices maybe that are not susceptible to fault injection. The problem is not everybody uses the latest and greatest stuff, and especially with the way that the semiconductor industry is going and the chip shortages, we might not be able to use the latest and greatest stuff. We might have to use what's available on the market, which are going to be robust devices that have been existing for a long time. So any device that's out there is going to be susceptible, which is kind of cool, right? It's like, yes, some people like hacking the latest things, but there are lots of vulnerable things that are still out there. Just like, Some people patch their computers, but most people don't. And that's how we get all of these ridiculous, software vulnerabilities and malware and ransomware and all this stuff, because people are not upgrading. Same thing with hardware. And it's a lot harder to upgrade hardware, right? It's like respinning silicon is not an easy task to fix a problem, which then somebody could still figure out some new attack against it. So it's definitely a cost, versus security trade-off. Anyway, so another method I was looking at is a lower level than looking at the user firmware. This is taking advantage of the actual boot ROM and the bootloader that's built into the STM32. So regardless of what version of firmware something is running, this attack will still let me get the entire flash memory contents. So some mitigations that Trezor has done since my attack and was based on, the earlier attacks, they've added encryption and other things. But ultimately it doesn't matter what's at the high level if your base is not secure. Right? It's just like the internet. It was never designed to be secure, but we're trying to patch it and make it secure because now we're all using it for secure things. Same thing with hardware. So they try to do things and mitigate things in software, in firmware, but at the lowest level, we can still exploit the chip itself to get all of the firmware off. And there's been some work about this published also through Kraken. They're using the serial bootloader. So using a UART interface to communicate, and there's like a read memory command. So you basically downgrade from RDP2 to RDP1, which enables the serial bootloader, which is different from the debug interface. And then there's a read memory command that you can send and read memory, and you have to also do a fault injection on that. So it's like a double fault injection. And each time you do a read memory command, it's 256 bytes. So you kind of have to get a lot of it if you're going to, grab the whole image. This also requires physically taking the chip off of a board and putting it into the socket, which is not really a big deal. It's just an extra step. So there's some other work I'm doing on this as well that hopefully I'll be able to release at some point. And of course, doing glitching using my chip whisperer. To do my serial interfacing, I'm using a USB to serial adapter so I can communicate from my computer, write the code I need to communicate to the target. And I'm using a device called the MUART. I call it micro UART, but it's basically a nice USB to serial adapter that has some voltage level shifters in there and some isolation, so you're not directly loading the pins and things. So it's kind of handy. You got that on Crowd Supply. And yeah, so here's a picture of like inside, you take the chip out, you put it in the socket, and now it actually breaks out all of the connections for you, and then you can connect up what you need. So one problem with the serial bootloader is because it's using an asynchronous serial interface, it's not synchronized to the clock, or I guess more specifically, the target who's communicating to it, which is me, is not synchronized to the chip. So when I send my command to read the data, the chip might have to do something else first before it actually responds to that because we're not synchronized at the same time. So we can see there's a lot of jitteriness when I'm sending my command and I'm doing a glitch, my fault injection, somewhere between sending the read command and getting the response back from the STM32 is when the check is happening. Is the user allowed to read memory? And there's like a 10 microsecond jitter, which is pretty significant. And it means that while sometimes you get lucky and you can read the contents, other times you get unlucky and you completely erase the flash. Because there's another command in the list, there's read memory, there's write memory, there's erase entire memory. And when you're glitching, you don't really know what you're hitting. And when there's jitter, you really don't know what you're hitting. So here's what it looks like. It's significant. So I do have some ideas of ways to mitigate that and reduce that. And that's something that if you're doing this on a real device, it would be nice to have things a little more stable because sometimes it works. You get all the data. Sometimes it doesn't. Which is great if you're just releasing information and telling people about it. But if you want to do it on a customer that maybe has a lot of money on it, that could change their life and you mess it up, that's kind of problematic. So yeah, definitely some fun things to do. I promised I would put some work on the ledger in here as well to be an equal opportunity hacker. And this is some work on a Ledger Nano S. And all these cameras are coming out. I'm just going to relish in this moment while you take pictures of it. So somebody contacted me and said, hey, I have a ledger. One of the buttons is broken and I can't press the button to do what I need to do because the ledger has two buttons left and right and you have to press both of them to enter things. And he didn't know what to do. He's like, I know my PIN, but I can't enter it. The ledger is not responding. So this is one I said, okay, if it's a mechanical failure of the switch, it shouldn't be too hard to fix. So this one, I was watching a teardown that, Dave Jones did, who runs the EEV blog, who had taken one of these things apart. So I was able to look at this before I even bought a ledger to look at and before the guy even sent me his ledger. I had already done my information gathering and kind of my research to know what I was getting into. And I could see, the switches were exposed. Here's the kind of general purpose microcontroller to do the UI front facing stuff, which is where the switches are connected to. And then there's the secure element, next to it, which is storing the, critical information. But I didn't care about this, right? Because we knew the pin. I just had to deal with that. So I knew where the switches were. I did a very quick reverse engineering once I bought one, to do my continuity testing and figure out where the switch went directly to the I/O pins of the microcontroller. And then verified when the guy sent me that his switch just wasn't working. There was just a mechanical failure in it, which is pretty amazing because these types of devices are designed to withstand hundreds of thousands or millions of presses, and it just failed, which is fine. So what I ended up doing is one of the ugliest hacks, but also one of the totally effective of basically bypassing the switch and just soldering on my own button to it, bypassing the one on the device, and then called up the customer and said, okay, the buttons work, and he told me his PIN, and I just entered, left and right, and entered things, and this is showing about to be the confirmation screen to actually free his money from the device. And I think that's kind of cool. Some of you might be thinking, well, that's not really a hack. That's kind of lame. It's just a button. But it shows that, hacking really to me is just like using the minimal amount of effort to get the job done. Maybe there was a different way, right? A more advanced way to get the contents out to free his funds. But this is really the hacker way, right? It's like looking for that simplest way to defeat the device to achieve the goal, which was to get the money off. It doesn't have to be a high profile attack every time, which I thought was kind of cool. And this didn't have nearly as much money as the Trezor, but it's equally as important. And it was equally as satisfying, possibly even more satisfying, because he was like, this is amazing. I didn't think I'd ever see the money. I'm, very thankful of this, with a super easy hack, right? So you can kind of see the variety. This was like 20 minutes versus 3 months. Here's another one. This was hacking a phone because, the customer had a Samsung Galaxy phone and he had forgotten his swipe password. There's a whole story behind it, but he basically bought Bitcoin a long time ago, ended up having a daughter and kind of got distracted, threw his phone in a box and forgot about it completely until Bitcoin started going way up. And he's like, wait, I think I bought Bitcoin. And he ended up finding the phone but couldn't remember his password. And this was one where he had thought that there would be maybe like multi-millions of dollars. So it was kind of exciting. I also liked it because it was using different techniques. And even though I've used the techniques a lot of times, it's still fun to do it on a different platform. So this one was, these were just showing my examples, my devices that I bought on eBay to kind of mimic his, but it's the swipe password that you kind of draw with your finger on an Android device. It turns out that this is a Samsung Galaxy S3, so an older version, but again, the age doesn't really matter because older devices are still out there and they're still vulnerable. This one was kind of cool because it actually had a tiny little JTAG connector exposed right when you pop the cover off. You just have to unscrew a couple screws. And there's a little JTAG connector right here, which is an industry standard debug interface that if you get access to it and it's not locked, that's your win. Just like with the Trezor, getting access to SWD is an ARM specific debug interface. But JTAG we see everywhere. Nowadays, it's more often locked than not, so you have to do fault injection or something else to enable it. But in this case, it was totally wide open. Only for the first like half a second when the phone booted, so you had to at least do that, try to connect to it and halt the device before it kept executing. Because this was an older device, I actually found this cable that I could use that attached to that tiny little connector, and then it connected up to my JTAG interface hardware. So in theory, I should have been able to just plug this in, run some software, dump all the code, and then once I had all of his data, the way that Android works is it's very, it's a Linux-based system and it has different partitions. So I could find the user partition. I could find where his gesture swipe password was stored and then compare that because that's a SHA-1 hash. I could compare that with a list of like a lookup table of all of the possible combinations and their SHA-1 hashes and compare. So in theory, it should have been really easy. But like with every project, except for the button, things that appear easy usually spiral out of control very quickly. So this wasn't working. I was getting some errors and I thought maybe it was a wiring error or something, communication error. I don't really know. So I was like, okay, maybe the cable's the problem. And I did continuity testing and everything and it seemed okay. Turns out that I made a mistake with that, but we'll get to that later. So I wanted to hardwire. I'm going to bypass that flexible cable altogether and I'm going to do tiny micro soldering from that connector to an adapter to see if I can actually detect JTAG at all. Because all of the forums are saying JTAG is there, but I couldn't see it yet. So I did this kind of hardwiring experiment. My first time really doing micro soldering. This is 0.1 millimeter diameter, like magnet wire, and had my microscope and doing it. Brought it out to an adapter, and then I used the JTAGulator, which is a tool that I designed back in 2013 that I had no expectation of having it still being manufactured and used today. Which is very cool. But it's a device that basically will query any unknown pins that you connect to it and emulate enough of the JTAG communication to see if there's a JTAG interface there, and then tell you which pins are the right ones. Because I can rely on this tool, and I didn't know about this, I wired it up, ran the tool, and I could actually verify, like, yes, there is a JTAG interface there. So then I said, okay, cool. Now that I know that the hardwiring works, I can then hook it up to a different debug interface. There's a lot of interesting like mobile phone hacking tools that are out there. The first one I used was the Riftbox. Second one I used was the Octoplus Pro. And they all have these weird like licensing requirements, or you buy credits from them on these like shady websites. It's really amazing that anything actually works, and that more people don't get ripped off. But the Riftbox software that I had, my license expired. So it's like, all right, so I wanted to find something that seemed maybe a little newer and more supported. So I got the Octoplus and wired it all up. This says bricked because during some of my other experiments through the USB interface, I was running some Samsung tools and just like completely screwed everything up. But it turns out I only wiped the operating system partitions, not the user data. So I was still able to properly test so that I could decode figure out what the swipe password was, which was kind of fun. And here's like, one of the screens showing that I could actually detect the two devices in that JTAG chain. So I could see that they're there. It's Qualcomm part MSN 8960. There's not a lot of information about these kind of mobile system on a chip devices, but these groups that are creating these tools are doing enough reverse engineering and somehow getting enough documentation to know how to communicate to the chip and then how to communicate from the chip over JTAG to deal with the external memory device. And in this case, we had the system on a chip, but then it's external eMMC, which is really nice because dealing with eMMC devices, it's a managed type of flash memory device. So a very simple interface, and it appears as like a block disk or a block device on your computer. So if you're able to get access to it, you can then kind of mount it and look around, which is really cool. Anyway, so yeah, it finally came up and I started doing my extraction. It's very, very slow, like up to 24 hours or so for like a 16 gig memory. But hacking isn't always about speed either, right? This is in my lab. There was no rush to try to do it faster. I would rather do it slower and safer and make sure that it was going to work. So I proved that this option worked over JTAG. That was kind of cool. But because this was a real project, I wanted to have a backup plan. What if that didn't work on the customer's phone that I was doing this on? So I wanted to have another option. And the other option is going directly to the eMMC and just reading the memory device in circuit and then manipulating the memory as I need to. So this is a picture from a digital camera I picked up on eBay. The link is at the end, which is pretty nice. And using that OctoPlus tool, they have an option for dealing with eMMC, and we'll even show you the pinouts where you need to connect to. A lot of times what people will do if they're in a desperate situation is just take the memory off of the board, put it into a socket, and then they can read the pins. A lot of eMMC devices have the same pinout, which is cool. But if you can not do that, that's better, right? We want to use that minimum possible attack to be successful. Taking the chip off is a huge risk. And in our case, we needed to just figure out the swipe password, but then he still had to log into his phone and get to the wallet. So taking this off just would have been a hassle. So this group had actually figured out which pins you need, or where the pins are and where the test points are to get to the connections of that eMMC, because these chips are ball grid array. All of the connections are balls of solder underneath the part, which makes hacking them like super annoying. So we had, basically for eMMC, you just need a command line, a clock line, and a single data line. And you can have more data lines if you want to read faster in parallel, but that's the cool thing about eMMC. You'll need ground as well, but you can power the target on its own, connect up your command clock data, send the right signals to the chip, and as long as the chip isn't being used by anything else at that time, it's just going to willingly just dump everything for you. Because chips are very trusting, unless there's like authentication or something. There's also the two power lines, which it turns out I didn't need, but you have two different voltage rails for eMMC. You have your like I/O voltages, and then you have your core voltage. So again, I did some micro soldering. I'm all about like, permanent connections if you can, because then it seems a little safer if you're moving stuff around, but I'll show you a non-permanent option also. So yeah, did some more micro soldering on a different device and soldered my tiny little wires up to a different pin out on the adapter, and then was able to communicate directly to the eMMC using the same tool, which was nice. And then I can actually see all the different partitions. The user data partition is like a little over 12 gigs, and that's where the swipe password is. And then I could extract everything that way. So once I knew I had two options, then I was ready to go and deal with the customer, which I'll show you what that looks like in a second. But here's the solderless way of accessing test points or components on a board. And this is a device called the VR table. We call it the spider table because it looks like a spider. And there's these arms that you can adjust, and you put these tiny spring-loaded pogo pins into the arms, and you move them around and place them down on where they need to be on the board. Super, super tiny. And then we have those wired up to the OctoPlus. So this was really the third option, right? If I couldn't do hardwiring for some reason on the customer's board, we had this option to do it. And here's part of the camera looking down. So ultimately, we got everything ready, and the customer did not want to leave his phone with me, because he was worried, right? Millions of dollars. And when with Dan's, we knew it was going to be we hoped it was going to be like a very quick kind of, multi-hour, but a single day attack. So he flew in and we did it. This one, because if we ended up using JTAG, it would have taken a lot of hours. So he just didn't want to come down and hang out for that long, which I don't really blame him. So we decided to go up to Seattle where he lived and set up a mobile hardware hacking lab in a hotel room. So that's what this is. I brought all of the stuff that I'm used to using, hoped that I wouldn't have to use any of it. And then this is a picture of like just using the camera. You can just see the awesome resolution. And it turns out there was a TV in the bedroom. So I'm just hooking that up directly. So it was like a nice ambiance, at the beginning. But it turned into quite an adventure. And I'm not going to tell you the result because this video is going to come out, in the next couple weeks. And it's very exciting, so I highly recommend that you watch it. So these are some of the resources of things that I've used just for these projects. And it's like, once you get these and mess around, you really do start looking at everything. And it's like, can I glitch that? Is there some other interface I can use? Like, is there some UART I can connect to? Like, there's so many fun things to do with hardware, and that's what keeps it exciting. Yeah, so I'll post these on my website, which is grandideastudio.com. I'll just put it on the main page or something so it'll be easy to find. And yeah, so that's it. Basically, like with all of this, hacking is something that I think almost more often than not requires a lot of patience, a lot of persistence. You need to really be passionate about it, whether it's a simple attack or not a simple attack. There's some like amazing talks over the next 2 days that are like mind-blowing types of stuff. And those didn't happen overnight, right? It was like a very determined person or group of people doing this stuff. But if you love it, that's the best part, right? To be able to do this stuff as a living, hacking on hardware is great. So, with that, I would say enjoy the conference, have fun, talk to each other, learn from each other, share with each other, and, yeah, keep on hacking. So, thank you. Enjoy the show. You wanna?
Thank you, Joe.
Do we have time for questions?
We can take one.
Okay. Okay.
Okay. Thank you very much for your presentation. It's very interesting. My name is Karim and I come from Ledger.
Yes.
Okay. I just have a question for Trezor attack. Did you perform any work on Trezor T or?
Did I perform any?
On Trezor T model?
Oh, on the Model T. No, so I haven't looked at the Model T yet. The Model 1 is a STM32F2, and then F4. The Model T is a 32... F4. I know they both have serial bootloader capability, so I have a feeling that it's going to be glitchable in that way, in that second method, but I haven't looked at it. I will if somebody comes to me and says, hey, there's money on this to make it worthwhile, but it's hard to given my schedule, to look at it to justify looking at otherwise, but I will, and it's kind of on my list. I'm ready when there's a motivating factor.
Okay. I have another question I can ask. Okay, you said that you already raised the memory while you are performing RDB2 or RDB1 to dump the flash. What did you do to make the attack with zero risk, for example?
For the first way?
No, for the second one.
Oh.
For the first one, I know that it's a very old firmware.
Yes, yeah.
So it's like a RDB2 and then...
Right, so for the bootloader, what did I do to reduce the risk? I'm not sure I can tell you that yet. But it's basically trying to get better synchronization between the commands and the device, right? So if I can synchronize me to the target, it's going to be a lot easier to control when I'm doing the glitch. That's the plan. And I have some other attacks that are not bootloader related, but more memory transfer related that may or may not work, depending on how ST has implemented some stuff. So there's some ideas that I want to try. Okay, so we have, well, you do it. I don't normally, I did a giveaway on a live stream to have somebody come to the class, which was hilariously awesome, and it worked. And Alex is here, I think. Hey, he came all the way from France. But doing a giveaway it was really funny because people were like, yeah, I can come. And then, we chose their name and they're like, oh, I can't come. So you can do it. You can give those away however you want, but we have some books, some really, really good books. So that means he get both.
Which one would you want? Okay, I think we're above time. So Joe, you can hang out in the kind of CTF area.
Yeah. I'll
take one more question for this.
Okay, just a quick one. Okay.
This one's for the Hardware Hacking Handbook by Colin and Jasper.
It's signed.
Signed.
This is probably a bit of a stupid question, but when you do the micro soldering for the wires, how do you make sure that there's no short on any of those wires? Do they connect, or is there a way that they don't short out? Yeah,
definitely not a stupid question. So that magnet wire has a thin coating of enamel around it, so they look like they're conductive, but they're not. So what you do is basically you stick the end of the wire onto your soldering iron with some solder on it, and either the flux or the solder like burns away a little bit, and then you can touch that down. But it's so easy to, at the ends, I mean, the stuff is so tiny that I was using the camera and then looking up at the screen to do some soldering, and I had my microscope really, really hard. But your hands do have a lot better resolution than you think when they're under magnifying, so you can do it. But yeah, that was always my question too, of like, how are these things not shorting? But it's enamel around it. And it just looks like a rat's nest, but it, seems to work usually.
All right. Thank
you.
Cool.
Yeah. Thank you again.